evening, class, and welcome to our final project presentation. We are group number 4. My name is Mario Dominguez.
Hi, my name is Maria Parra. This is group number 4, and I hope you enjoy our presentation.
And last but not least, I'm the last member of this group. My name is John James Murphy. I'm a mechanical engineer student, and this is my last year, hopefully. And yeah, enjoy the video.
In this final project, we were assigned to simulate the parts of an engine. In this case, we performed static, buckling, and thermal studies in order to evaluate the mechanical behavior of these components under various forces and conditions. Starting off with the piston, we performed a compressive static study using aluminum 4032 T6 as a material. We used the standard default mesh for our study, as well as applying a fixture to the holes where the piston pin is held, and an external load with gravity and pressure force of 130 psi. We also performed thermal studies. For steady state, we applied a temperature of 523.15 Kelvin at the top of the piston, followed by convection in the exposed outer surface using convection coefficient of 500, with an ambient temperature of 298.15 Kelvin. We obtained a minimum temperature of 417 Kelvin and a max of 523.15 Kelvin. For the transient thermal study, we applied an initial temperature of 298.15 Kelvin, then applying a temperature of 523.15 Kelvin at the top of the piston, using the same convection coefficient as the steady state, with an ambient temperature of 200 Kelvin. The total time was 5 seconds, with an increment of 1 second in order to find the temperature difference of the piston in matter of time. In this case, the max temperature remains the same throughout the whole simulation. However, the minimum temperature decreases as time goes by. Our next part is the piston pin, in which we perform a bending study, which seemed complex as we had to split the piston pin, which both sides are fixed due to its holding with the piston, as well as applying gravity downwards and a force of 20,000 newtons in the middle due to the compression coming from the piston and the motion of the connecting rod.
Our next part is the connecting rod. We did a compression study, and for material we used cast alloy steel and a load of 3,621 newtons. This load was applied in two parts of the rod, in the bushing where the piston pin rests, as well as in the big end where it is connecting to the rod cap. This load was determined by the 130 psi the piston head was under. The rod was also fixed where the screws go and in the arch where it is supported by the crankshaft. For this same part, we did a bending test using the same material and the same forces. But in this case, with the forces had a 17.5 degree angle, simulating the rotation that this connecting rod is under inside the engine. We also did a buckling test with the same conditions as before, and the load factor given by SolidWorks was 38.5, meaning the critical load for the rod is about 139,000 newtons. We also did a design study using the static study for the connecting rod compression test, as it would be optimal to try different materials for the part to have a higher factor of safety. We tested different materials, such as titanium, which did increase the factor of safety to 12, making it a better option, but also a more expensive one. We opted out to use cold-rolled steel, which increased the factor of safety to 8.2, not as high as titanium, but a cheaper option.
My role in this project focused on analyzing the crankshaft's behavior under bending and torsion, using AISI 1045 steel for its strength and cost effectiveness. We simulated realistic engine conditions. In the bending study, a 10,000 Newton downward force on a single pin and gravity were applied to replicate a firing piston. The results showed a maximum stress of 11.2589 million pascals and a minimal displacement of 1.45 millimeters, demonstrating the crankshaft durability. For the torsion study, a 4,000 Newton meters torque was applied, reflecting twisting forces from piston combustion. This produced a maximum stress of 427.195 million pascals, with a safety factor of 1.2. Critical stress points near the pins highlighted potential areas for improvement, and these simulations confirmed the crankshaft reliability under high stress conditions and provided insights to optimize its design further.